There was no problems with powering something with nickel hydrogen batteries. Second, we decided to bring the computer resources package because it said within the question that it was prior to repurposing the resupply of the ISS with critical hardware. So we wanted to allow to have critical hardware, which we considered computer resources package part of critical hardware. The third thing was operational systems equipment package. We decided to bring this mainly because we deem this as critical hardware, the same reasoning as number 2. So I'm going to hand it off to Devin to allow for more things that we decided to not bring to.
Okay, right. So again, with the EVA supplies, which next, you can see that we've decided not to bring this on our mission. And the main justification for this is just like the nickel hydrogen batteries, we didn't find any evidence directly correlating with an actual problem that we were given. So we decided to move on the prioritization of what we were given. And given that, we also see that the next one, the crew food personnel crew items package, we also we opted out of bringing that. And another justification for that was it was specifically stated that it wasn't manned in the Orion capsule, and we also felt like this wasn't absolutely necessary given what we were also given as well. So the next thing on our thing is the cooling, our list was the cooling pump module. Obviously, we wanted to bring this because they were actually taking one out of the reserves, and we needed that as well as the ammonia cylinders. We deemed this as the central problem, and because of that, we wanted to put this on highest priority, so that's what we did include. That's why it's yes. The next is the CO2 scrubbers and filters. We also deemed this a necessary component of the space shuttle, and the main justification for this is that if there's already a problem on the shuttle, we need to have contingencies for the safety of the ones, as well as any other issues to prevent that. We felt that was absolutely essential. So with that, I'm going to pass on to Aaron to justify.
So for the original payload, we decided, since this was a lunar mission, we just wanted to bring stuff that had any prioritization towards a lunar mission. So obviously the NASA Research Laboratory package, which considered a research portion for a Mars mission, was not deemed necessary because we were not going to Mars. Therefore, for second to the NASA Research package, laboratory package was about ion radiation experimental package. So again, this wasn't deemed necessary because we didn't have a problem with ion radiation. Thirdly, the National Research Laboratory package, we didn't deem this necessary because it had to deal with the weather experiment, and the moon doesn't have weather, so we didn't deem that anything for a lunar mission. The ones that we did deem for this lunar mission was the National Research Laboratory package 2 and 3, because they were completely relevant towards a lunar mission because they were specifically stated within the question that was a moon laser interferometry package and a lunar gravity survey experimental package. So we deem those as such, and again, the rest of them, the education research packages 1 and 2, and the national research package number 4 had nothing to do with a lunar mission Mars. So now I'm going to be passing it on to Josh, where he's going to be proving why we justified bringing these certain items on our mission.
Okay. So essentially, when we were going through the problem for part 1, we wanted to make sure that everything would fit, because if it doesn't fit, we obviously cannot bring it. So the cubic volume was able to hold 385 cubic feet for the requested items that were listed, and then that was for the original items. The requested items are able to hold 348.75 cubic feet. So that does fulfill the volume capacity, because that is obviously less than the original number. The surface module mass holds 12,377 kilograms, which is a lot more than needed, which is only 2,932 kilograms. And we calculated this by adding up all the weights provided, and then the previous payload items do fit essentially under the requirements, because we made those calculations to ensure that the ones that we want to bring are under the original and the total capacity.
So now we're going to be moving on towards part 2, where Andrew is going to be explaining how he came up with the solution.
So basically for part 2, we had to find the change of velocity, also the insert velocity and the ejection velocity to reach the moon. So these are the constants we were given. We were given mu e, the GM of Earth, 3.98 by 10 to the 14th power. Mu m, the GM of the moon, 4.903 by 10 to the 12th power. The lower Earth orbit radius, 200 kilometers, and the lower moon orbit radius, 100 kilometers. Where AM is also also defined in the semi-major axis. So moving on, I'll have Ben explain the first three calculations.
We got the velocity per g by adding 2m uv. Basically, just plugged in all the numbers together. We added potential and kinetic energy.
Yeah, these are the calculated values we received. The velocity of the lower Earth orbit was achieved by the formula given. The velocity p was also achieved by the formula given, which gives our total change in velocity the inject for vp minus v of the lower Earth orbit to be 6,035.2 meters per second. Moving on, we found the velocity of the lower lunar orbit, which proved to be 7,002.143 meters per second. Continuing on, we have the velocity m equal to the velocity of the lunar orbit, that is, equal to, once you plug in the values, 33,140.473 meters per second, and velocity of the p equal to 27,936.185 meters per second. So that gives that RVL equal to 11,182.16 meters per second, and the change in velocity of the insert 4,180.01 meters per second. These are the calculated values. Moving on, we had part 2, which use the whiteboard if you don't mind too much. So for the part 2, we have the delta V budgeting. This part is just adding up the total for the velocity inject and the velocity insert. So we add up 6,035.2 meters per second and 4,180.01 meters per second to achieve our total change in velocity to be 10,215.21 meters per second. Moving on. Okay, for problem 2, I believe it asked. Problem 3. Okay, for problem 3, it asked for a specific impulse in kilometers per second. So the formula for the impulse was impulse was equal to the impulse was equal to the velocity of the exhaust exiting divided by the g, where g is the gravitational constant for Earth at 32.2 meters per second squared, or feet per second squared, excuse me. So the impulse was given to be 421 seconds, and that equals the velocity of the exhaust divided by 32.2. So we end up with our value for velocity of the exhaust to be 13,550 meters per second squared, or the final velocity, or 13,550 meters per second, excuse me. And our final velocity was 13.55 kilometers per second. So we have to convert it to kilometers. Moving on, problem 4, we have thrust, and they gave us thrust. They gave the thrust formula to be thrust equals force times velocity, force by velocity. So if thrust equals force by velocity, we have the velocity of the exhaust to be 13,550. Thrust is in kilogram meters per second squared because it's with newtons. So we have 294,000 LBF, and I didn't keep 294,000, and that equals the force multiplied by the velocity of the exhaust. So that's force by 13,550. So if this is measured in kilogram meters per second squared, and this was measured in meters per second, some dimensional analysis will give us kilograms per second, because the meters cancel and the seconds cancel once. So you end up with the force equal to, or the flow rate, equal to 21.687. I think it's kind of force the whole time. I meant to say flow rate each time. Alright, so you end up with a flow rate equal to 21.687 kilograms per second. Finally, with problem 5, we have this formula they give us, which is the change in velocity is equal to the velocity of the exhaust multiplied by the natural log of the ratio of the initial mass over the final mass. So given the delta V budget, we calculated calculated the desired ratio of the initial mass to the final mass to be 2.125. Moving on. Moving on, this proves that given the propellant mass is equal to the final mass multiplied by the e to the power of the change in velocity over the velocity of the exhaust minus 1, we calculated that the propellant mass should be 1.12 of the final mass, or 1.12 times the final mass, which equates to about 53% of the initial mass. So taking in regards to part 1 and how we're supposed to properly store all this propellant and all this fuel, basically we were only allotted around 47% of what we had given to the rest of the necessities besides the propellant. So basically, knowing that we were well under the weight needed, I believe the maximum weight was about 12,000 something, and we received about 2,000. We were able to add on this extra propellant, which would allow us to go. So that was our final conclusion.
Right. And also, so considering this justification, also just to wrap it all up, essentially what we did when we looked at prioritizing our list, we did choose the ones that, first of all, that we deemed essential, but we also made sure to focus on the actual question itself. And when we prioritized this, we saw the problem first, that was priority 1, and then essential ones that were stated and mentioned in the questions, and then as followed, and then the ones that we didn't keep were either because we didn't see them in the question, or we simply did not have enough weight according to these calculations. So in the end, that's how we justified most of the answers, and the calculations are there to justify them. Thank you.
Thank you.
Would you like to see any of our calculations at all? Okay.
Thank you so much. Thank you for judging as well.
Thanks for using the comment.
Thank you so much. Good job, guys. Thank you. Thank you. Yeah, that one's